Hey, sleepers. Tonight, we're sinking into one of the deepest and most familiar mysteries of all. We are surrounded by it. We live within it. It feels like a river, carrying us from the past, through the present, and into the future. Look up at the night sky. The moon hangs there, a silent, glowing clock. Each star is a distant beacon, its light having traveled for years, for centuries, for millennia, to reach your eyes right now. The entire universe is a quiet, sprawling testament to the passage of something we call time. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you feel like it, I would love to know where you're listening from. Go ahead and type your city or country and your local time in the comments. It's always a quiet joy to see how this single moment is shared across so many different points on our spinning world, each with its own number on the clock. So close your eyes, take a deep breath, and get ready to drift off as we explore. What is time, really? Let's begin with a feeling. The feeling of waiting for a kettle to boil. The feeling of a cherished memory. The feeling of looking forward to a quiet weekend. This is our human experience of time. It feels like a straight line, a one-way street. We remember the past. We live in the present. We anticipate the future. This is what physicists call the arrow of time. It points in only one direction, forward. You can remember breaking an egg to make an omelet. But you will never see an omelet spontaneously unscramble itself back into a perfect, unbroken egg. This forward flow, this inability to unbreak the egg, is one of the most profound and simple truths of our universe. It is a concept called entropy, the idea that things on a large scale tend to move from order to disorder. A neat stack of papers is more likely to be scattered by a breeze than a scattered pile is to be neatly stacked by one. The universe, it seems, loves a bit of a mess. And this constant, gentle slide towards messiness gives time its direction. It's why yesterday is always behind us, and tomorrow is always ahead. But how did we begin to measure this invisible flow? How did we capture something so abstract and put it on our wrists, on our walls, on our screens? Our journey with timekeeping began, as so many things did, with the sky. The first clock was the world itself. The sun would rise in the east. This marked the beginning of the day. It would travel across the sky. Its highest point marked midday. It would set in the west. This marked the end of the day. Then came the moon, with its own gentle, predictable cycle of waxing and waning, giving us the concept of a month. And the Earth's own journey around the sun, bringing with it the slow, grand shift of the seasons, gave us the year. This was nature's clock. It was big. It was reliable. And for a very long time, it was all we needed. It told our ancestors when to plant, when to harvest, when to hunt, and when to rest. It was a rhythm woven into the fabric of life itself. Then we began to want more detail. We wanted to divide the day. The ancient Egyptians and Babylonians gave us one of the first pieces of timekeeping technology. It was simple, elegant, and powered by the sun. It was the sundial. Imagine a flat disk with markings around the edge, and in the center, a stick or a pillar called a gnomon. As the sun moved across the sky, the gnomon would cast a shadow. This shadow would creep slowly across the marked disk. It was like a silent, steady finger pointing to the hour. For the first time, people could look at an object and know with reasonable accuracy what part of the day it was. It was a marvel, but the sundial had its weaknesses. What happened on a cloudy day? the clock would stop. What happened at night? The clock was useless. Humanity needed a clock that worked indoors, a clock that worked in the dark. This need gave birth to the water clock, or as the ancient Greeks called it, the clepsydra, which means water thief. It's a beautifully simple idea. Imagine two containers, one placed above the other. The top container is filled with water. At its base, there is a tiny hole. Water drips out of this hole, slowly, steadily, into the container below. The container below has lines marked on the inside. As the water level rises, it passes these lines, indicating that a certain amount of time has passed. It was a continuous, flowing measure of time. It wasn't dependent on the sun. It could be used day or night, rain or shine. In ancient Athens, water clocks were used to time speeches in law courts. Each speaker was given a certain amount of water. When your water ran out, your time was up. A rather elegant way to stop people from talking for too long. A man named Ctesibius of Alexandria, a brilliant Greek inventor and mathematician living around 250 BC, made incredible improvements to the water clock. He created intricate versions with gears and dials, and even little figurines that would move and point to the hour. He was a master of turning a simple drip of water into a sophisticated machine. And then there was the hourglass. Another wonderfully simple device. Two glass bulbs connected by a narrow neck. Sand, fine and dry, flows from the top bulb to the bottom. Like the water clock, it measures a specific duration, but it was more portable, more robust. You could see the time remaining, the sand slipping away grain by grain. It became a symbol of time itself, a reminder of its constant, unstoppable passage. Sailors used them on long voyages to measure shifts and calculate their position. Monks used them to mark times for prayer. For centuries, these were our best tools. Water and sand, flowing under the steady pull of gravity, were our timekeepers. But society was changing. The world was becoming more connected, more complex. The rise of trade, of industry, of railways demanded something better, something more precise, something that could be synchronized across great distances. This led to the age of the mechanical clock. This was a tremendous leap forward. Instead of relying on the flow of water or sand, these clocks relied on the intricate dance of gears and springs. The true genius was a device called the escapement. The escapement is what makes a clock tick. Imagine a coiled spring, full of energy, wanting to unwind all at once. The escapement is a clever little mechanism that stops it. It escapes the energy in tiny, regular, controlled bursts. With each burst, a pendulum swings or a balance wheel turns. And with each swing or turn, the hands of the clock move forward just a little bit. Tick, tock, tick, tock. This was the sound of a new era, the sound of precision. The first mechanical clocks were huge things, housed in the towers of churches and town halls. They were public clocks for everyone. They chimed the hour, organizing the day for an entire community. People began to live by the clock, not just by the sun. Work started at a specific time. Shopkeepers opened at a specific time. Trains, this amazing new form of transport, had to run on a strict schedule. This need for synchronized time across countries led to the creation of time zones. The world was carved up into 24 slices, each with its own coordinated time. It was a global agreement, a shared rhythm that allowed the modern world to function. The quest for ever greater precision continued. Clockmakers became celebrated artisans. They built beautiful, intricate timepieces for the wealthy. Scientists needed even more accuracy for their experiments. Navigators at sea needed hyper-accurate clocks, called chronometers, to determine their longitude and avoid crashing into rocks. A man named John Harrison, a humble English carpenter, dedicated his life to this problem, and after decades of work, created a marine chronometer so accurate it changed navigation forever. His clocks were masterpieces of brass and steel, able to keep near-perfect time even on a rocking, rolling ship in the middle of the ocean. But even the best mechanical clock has its limits. Temperature can make its metal parts expand or contract. Friction wears down the gears. The pull of gravity can vary slightly from place to place. For most of human history, these tiny imperfections didn't matter. But in the 20th century, science began to probe the universe at a scale so small and a scale so large that we needed a clock of almost unimaginable accuracy. We needed a clock that was not based on something man-made, but on a fundamental property of the universe itself. This led to the invention of the atomic clock. The concept is both simple and mind-boggling. Instead of a swinging pendulum, an atomic clock uses the vibration of an atom. Specifically, an atom of an element called cesium. Atoms don't just sit still. Their electrons can be encouraged, using microwaves, to jump between two very specific energy levels. And when they do, they oscillate, or vibrate, at a perfectly regular frequency. They are the universe's most perfect pendulums. A single cesium atom, under the right conditions, will oscillate exactly 9,192,631,770 times per second. Every single second. It doesn't get tired. It doesn't wear out. It's a constant, provided by nature itself. A British physicist named Louis Essen, working with his colleague Jack Perry at the National Physical Laboratory in 1955, built the first practical and accurate cesium atomic clock. Their work was revolutionary. It was so accurate that it became the new official standard for what a second is. The very definition of our base unit of time was no longer tied to the spin of the Earth, which can wobble and slow down ever so slightly. It was now tied to the unwavering dance of an atom. Today, the atomic clocks that form our global time standard are so precise that they would not lose or gain a single second in over 300 million years. This incredible accuracy is not just an academic curiosity. It is essential for the modern world. It is what allows technologies like the Global Positioning System, or GPS, to work. We will return to this because the story of GPS is deeply connected to our modern understanding of time. This vast history, from a shadow on the ground to the vibration of a single atom, shows our relentless drive to measure, to quantify, and to understand the world. But all of this history, all of these clocks, are based on one simple, powerful, and deeply intuitive idea. An idea that was the foundation of physics for centuries. An idea that was championed by one of the greatest minds in history, Sir Isaac Newton. And it is this idea that we will now explore. The idea of absolute time. So let yourself settle deeper. Feel the gentle weight of your body. Notice the quiet rhythm of your own breath. Your heart beats, a personal, steady clock. Let's drift back to the 17th century. To England. Imagine a world lit by candles and firelight. A world of quill pens and ink, of grand universities, and blossoming scientific curiosity. This is the world of Isaac Newton. Newton was a giant of science. He gave us the laws of motion. He gave us the law of universal gravitation. He figured out that white light is made of a rainbow of colors. His mind reshaped our understanding of the cosmos. And at the heart of his entire system, at the foundation of all his beautiful equations, was his idea of time. For Newton, time was simple. It was absolute. What did he mean by that? He meant that somewhere, out there was a single universal clock for the entire cosmos, a master clock. This clock ticked away at a perfectly steady rate. 1 second was 1 second. Everywhere, for everyone. It didn't matter if you were sitting still, reading a book. It didn't matter if you were galloping on a horse. It didn't matter if you were on Earth, or on the moon, or on a distant planet orbiting a distant star. Time flowed at the same rate for all of them. It was a single, immense, invisible river, carrying the whole universe along at a constant speed. Newton called it absolute, true, and mathematical time. It flowed, in his words, equably without relation to anything external. It was the ultimate background, the stage on which the entire drama of the universe played out. Let's try a little visualization. Imagine you are floating in the vast, quiet emptiness of space. There are no planets, no stars, no galaxies. Just you in the silent dark. But you can hear something, a sound, a gentle, steady beat. A cosmic drum. Boom, boom, boom. Each beat is a second. This drum is Newton's absolute time. Now, imagine a star appears in the distance. The beat continues. Boom, boom, boom. Unchanged, a planet begins to orbit the star. The beat continues. Boom, boom, boom. Unchanged, you start to fly through this space, moving faster and faster. The beat in your ears remains perfectly steady. Boom, boom, boom. Unchanged. This was Newton's universe. Time was the ultimate constant. It was independent. It was separate from space. It was the universal metronome against which all motion and all events were measured. This idea is incredibly intuitive. It's how we experience the world every day. When you arrange to meet a friend at 3 o'clock, you both assume that your 3 o'clock is the same as their 3 o'clock. You assume that the minutes will pass at the same rate for both of you, whether one of you is driving and the other is waiting. Newton's absolute time is the time of common sense. And for hundreds of years, it worked perfectly. His laws of motion, which are based on this idea, could predict the path of a cannonball. They could predict the orbits of the planets. They could explain why an apple falls from a tree. The universe, in this view, was a magnificent, predictable machine, a giant clockwork mechanism. If you knew the position and speed of every particle at one moment, you could, in principle, calculate its entire future and its entire past. It was all set in motion, ticking away to the beat of absolute time. The development of better and better mechanical clocks seemed to confirm this idea. As clocks became more precise, they seemed to be getting closer and closer to measuring this true universal time. The steady tick-tock of a grandfather clock in a quiet hall was like a small echo of that great cosmic drumbeat. The synchronized railway clocks, all pointing to the same minute across a vast country, reinforced the idea that now was a single shared instant for everyone. It was a comforting thought. The universe was orderly. It was rational. It followed laws that we could discover and understand. And time was the reliable, unchanging ruler we used to measure it all. Think about the simple formula for speed. Speed equals distance divided by time. If you travel 60 miles in 1 hour, your speed is 60 miles per hour. In Newton's world, the time part of that equation was solid. It was fixed. 1 hour was 1 hour, pure and simple. The only things that could change were your speed and the distance you traveled. Time itself was off limits. It was the bedrock. This made the physics of motion relatively straightforward. It provided a stable framework for science for over 200 years. From the Industrial Revolution to the great scientific discoveries of the 18th and 19th centuries, Newton's clockwork universe, marching to the beat of absolute time, was the reigning picture of reality. It was a beautiful and elegant picture. But science is a restless endeavor. It is always pushing at the edges of what we know. It is always asking, is that really how it works? Can we test it? And in the late 19th century, a few strange cracks began to appear in Newton's perfect clockwork facade. These cracks came from an unexpected place, not from the study of motion or gravity, but from the study of light and electricity and magnetism. A brilliant Scottish scientist named James Clerk Maxwell developed a set of equations that beautifully described how these forces worked. His equations were incredibly successful. They predicted the existence of radio waves. They are the foundation of all modern electronics. But buried within them was something very, very strange. Maxwell's equations predicted that the speed of light in a vacuum was a constant, a very specific number, about 186,000 miles per second, or 300,000 kilometers per second. This didn't seem so strange at first. But then physicists started to think about what it really meant. A constant speed? Relative to what? Usually, speeds are relative. If you are on a train moving at 50 miles per hour and you throw a ball forward at 10 miles per hour, someone standing on the ground would see the ball moving at 60 miles per hour. You just add the speeds. That's common sense. That's Newton's world. But Maxwell's equation seemed to say that if you were on a spaceship moving at half the speed of light and you shone a flashlight forward, the light from that flashlight would not be moving at 1.5 times the speed of light. It would still be moving at the speed of light. Someone on the ground would see it moving at the exact same speed as you would on the spaceship. This was a major puzzle. It made no sense. It was as if the ball you threw on the train was seen to be moving at 10 miles per hour by you, and also at 10 miles per hour by the person on the ground. How could this be? How could the speed of light be the same for all observers, no matter how fast they were moving? It broke the simple rules of adding speeds. It was a direct conflict between the laws of motion and the new laws of light. Physicists tried to find a way around it. They proposed that there was a mysterious, invisible substance filling all of space, called the luminiferous ether, and that the speed of light was constant only relative to this ether. But experiment after experiment failed to find any evidence of this ether. The puzzle remained. The universe had presented science with a deep paradox. Either Newton's simple rules of motion were wrong, or Maxwell's brilliant equations of light were wrong, or perhaps something even more fundamental, something everyone had taken for granted, was wrong. Something like Newton's idea of a steady, absolute, universal time. And it would take a young, unknown patent clerk in Bern, Switzerland, to see the solution. A young man who had the audacity to imagine what would happen if the constant speed of light was the true, unbreakable law of the universe, and time itself was the thing that had to bend. His name was Albert Einstein. The shift from Newton's time to Einstein's time is one of the greatest revolutions in the history of thought. It asks us to let go of our most basic intuitions. It asks us to accept that the steady ticking of the clock we imagine for the universe is just an illusion. So let's take another slow, deep breath. Let the air fill your lungs. And as you exhale, let go of the idea of the cosmic drum. Let go of the single universal river of time. We are about to step into a new reality. A reality that is stranger, more flexible, and in many ways, more beautiful than the one Newton imagined. It is the year 1905. Albert Einstein, working as an examiner at the Swiss Patent Office, has a lot of time to think. He is not a famous professor. He is a young man with a deep curiosity about the world. He is wrestling with that paradox of light. How can its speed be constant for everyone? He realizes that everyone's measurements of distance and time are based on sending signals back and forth, and the ultimate signal is light. So, what if the constancy of light speed is the one thing that is truly absolute? What would that mean for everything else? He performs what he calls Gedankenexperiments, thought experiments. He imagines scenarios in his mind and follows them to their logical conclusions. And these thought experiments lead him to a stunning conclusion. If the speed of light is constant, then time cannot be. This is the core of his special theory of relativity, a theory of time and space without gravity. It rests on two simple ideas, or postulates. 1. The laws of physics are the same for everyone in uniform motion. 2. The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. From these two simple-sounding ideas, a whole new universe unfolds. A universe where time is personal, where time is relative. Let's try one of Einstein's thought experiments. It's the most famous one for explaining this idea, and it's called the light clock. Imagine a clock that consists of two mirrors facing each other. A single particle of light, a photon, is bouncing between them. Each time the photon hits a mirror, the clock ticks. Let's say the mirrors are 1 foot apart. The photon travels 1 foot up, ticks, and 1 foot down, ticks. Simple enough. Now let's put this clock on a transparent spaceship and watch it fly past us at a very high speed, close to the speed of light. From our perspective, standing still on the ground, what do we see? We don't see the photon going straight up and down anymore. Because the clock is moving, the photon has to travel a longer, diagonal path to get from the bottom mirror to the top mirror, and then another long diagonal path to get back down. Here is the crucial part. We both agree on the speed of light. That's the one unbreakable rule. So, if the photon in the moving clock has to travel a longer distance, but its speed is the same, it must take more time to complete its journey. From our perspective on the ground, the moving clock is ticking more slowly than an identical clock sitting next to us. Tick dot 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 tock, dot dot tock. The rhythm is slower. The rhythm is slower. And this is not a mechanical illusion. It's not that the clock is broken. The person on the spaceship sees their clock working perfectly fine. For them, the photon is just going straight up and down. It is time itself that has slowed down for the moving clock, relative to the stationary clock. This effect is called time dilation. Moving clocks run slow. The faster you move through space, the slower you move through time. This is a very real effect. But at the speeds we experience in our everyday lives, it is ridiculously small. So small that we could never notice it. If you were on a jet plane for a few hours, Your personal time would have slowed down by a few billionths of a second compared to someone on the ground, utterly insignificant. But if you could travel in a spaceship at, say, 99% of the speed of light, the effect would be dramatic. You could travel for what feels like 5 years to you, and when you return to Earth, you might find that 50 years had passed. All your friends would be old. The world would have changed. You would have traveled into the future. This isn't science fiction. This is a direct consequence of the physics of our universe. This leads to another strange consequence, the idea of now. In Newton's world, now was a single universal instant. We could all agree on what was happening right now across the entire universe. But in Einstein's world, simultaneity is relative. Let's try another thought experiment. Imagine a very long, very fast train. Exactly in the middle of the train, a light bulb flashes. For a person standing in the middle of that train, the light reaches the front of the train and the back of the train at the exact same moment. For them, those two events are simultaneous. Now, imagine someone standing on the ground, watching this train zoom past. From their perspective, the back of the train is moving towards the point where the light was emitted. The front of the train is moving away from it. So, the light traveling to the back has a shorter distance to cover than the light traveling to the front. From the ground observer's point of view, the light hits the back of the train first. The two events are not simultaneous. Who is right? The person on the train or the person on the ground? Einstein's answer is that they both are. Now is not universal. My now might not be the same as your now if we are moving relative to each other. We each have our own slice of time. We are each moving through a unified fabric that Einstein called space-time. He realized that space and time are not separate things, as Newton thought. They are intricately woven together. A single four-dimensional continuum. 3 dimensions of space, length, width, height, and 1 dimension of time. And our motion through space affects our motion through time. They are linked. This was the special theory of relativity. It was a masterpiece. It resolved the paradox of the speed of light. But it was incomplete. It dealt with uniform motion, moving in a straight line at a constant speed. But what about acceleration? What about gravity? It took Einstein another 10 years of intense, grueling work to incorporate gravity into his new picture of the universe. And the result was his general theory of relativity, published in 1915. It is perhaps the most beautiful and profound theory in all of science. And it changed our understanding of time even more deeply. Einstein had a moment of insight that he called his happiest thought. He realized that a person in a closed box, like an elevator, cannot tell the difference between being at rest in a gravitational field, like on Earth, and being accelerated in empty space. If the elevator is on Earth, you feel your weight on the floor. If the elevator is in deep space, far from any planet, and is being pulled upwards by a cable at just the right acceleration, you will feel the exact same weight on the floor. Gravity and acceleration are, in a sense, equivalent. This was the key. He then reasoned that if acceleration could affect space-time, then gravity must be able to affect space-time. This led to his revolutionary idea about gravity. Gravity, he said, is not a force pulling objects towards each other, as Newton had described. Gravity is a curvature, or a warping, of the fabric of space-time itself. This is the famous analogy of the bowling ball on a trampoline. Imagine space-time is a flat, stretched rubber sheet. If you place a heavy object, like a bowling ball, representing the sun, onto the sheet, it creates a deep dip, a curve in the fabric. Now, if you roll a smaller marble, representing the earth nearby, it doesn't get pulled towards the bowling ball. It simply follows the curve in the sheet, created by the bowling ball's mass. It orbits the bowling ball because that is the straightest possible path through the curved space. This is gravity. It is the geometry of space-time. Now remember, time is part of the space-time fabric. So if mass and energy can curve space, they must also be able to curve or stretch time. General relativity predicts that time flows more slowly in stronger gravitational fields. The deeper you are in a gravity well, the slower your clock will tick compared to a clock in a weaker gravitational field. This effect is called gravitational time dilation. It means that a clock at sea level, which is closer to the center of the Earth, and in a slightly stronger gravitational field, will tick ever so slightly slower than a clock on top of a mountain. A person living on the top floor of a skyscraper will age a tiny, tiny fraction of a second faster than a person living on the ground floor. Again, like the effects of special relativity, this is a real measurable phenomenon. For our everyday lives, it's completely negligible, but it has profound implications. It means the time at the surface of the sun flows more slowly than time on Earth. Time near a very dense object, like a neutron star, would slow down dramatically. And at the edge of a black hole, at a point called the event horizon, the curvature of space-time is so extreme that time, from the perspective of an outside observer, would appear to stop altogether. Time itself is bent by gravity. So we have these two incredible, mind-bending ideas from Einstein. From special relativity, moving clocks run slow. From general relativity, clocks in strong gravity run slow. This seems like wild speculation, like something from a dream. How could we possibly know if this is true? The answer is that we have tested it, and the predictions have been confirmed with astonishing accuracy. One of the first and most direct tests was an experiment conducted in 1971 by two physicists, Joseph Haffel and Richard Keating. It was beautifully simple in its concept. They took several incredibly precise atomic clocks, the kind we talked about earlier. They synchronized them all with a master clock at the U.S. Naval Observatory in Washington, D.C. Then, they put some of the clocks on commercial airplanes and flew them around the world. One set of clocks flew eastward with the rotation of the Earth. The other set flew westward against the rotation of the Earth. After the flights, they brought the clocks back to the observatory and compared them to the master clock that had stayed on the ground. What did they expect to find? According to Einstein, two things should have happened. First, because the clocks on the planes were moving at high speed relative to the clock on the ground, special relativity predicted their time should have slowed down, the moving clocks run slow effect. Second, because the planes were flying at high altitude, they were in a slightly weaker gravitational field than the clock on the ground. General relativity predicted their time should have sped up. The gravity makes time faster effect. The eastward flying clocks had a higher speed relative to the center of the Earth, so the time-slowing effect of speed was expected to be dominant. The westward flying clocks had a lower speed, so the time-speeding up effect of gravity was expected to be dominant. When they compared the clocks, the results were exactly as Einstein's theories predicted. The eastward flying clocks had lost a tiny amount of time, about 59 nanoseconds. The westward flying clocks had gained a tiny amount of time, about 273 nanoseconds. A nanosecond is a billionth of a second, an impossibly small amount of time. But the atomic clocks were sensitive enough to measure it, and the measurements matched the predictions. It was a stunning confirmation. Time really does change with speed and gravity. Newton's absolute universal clock was gone. Einstein's flexible, relative time was real. But you don't need to fly an atomic clock around the world to see the proof. Many of us use proof of relativity every single day. If you have ever used a GPS on your phone or in your car, you have used Einstein's theories of relativity. The Global Positioning System is a network of about 30 satellites orbiting the Earth. Each satellite has a very precise atomic clock on board. Your phone or GPS receiver on the ground works by picking up signals from several of these satellites. By measuring the exact time it takes for the signal from each satellite to reach it, your receiver can calculate its precise location on Earth. For this to work, the timing has to be incredibly accurate. An error of just a few nanoseconds can translate into an error of many feet on the ground. And here's where relativity comes in. The GPS satellites are in a situation just like the clocks in the Haefel-Keating experiment. They are moving very fast, about 8,700 miles per hour. According to special relativity, their clock should slow down by about 7 microseconds, or 7,000 nanoseconds, every day compared to clocks on Earth. But they are also orbiting high above the Earth, about 12,550 miles up, where gravity is much weaker. According to general relativity, this should cause their clocks to speed up by about 45 microseconds every day. When you combine the two effects, the speeding up from weaker gravity is stronger than the slowing down from high speed. The net result is that the clocks on the GPS satellites ran faster than clocks on the ground by about 38 microseconds every single day, 38 millionths of a second. It doesn't sound like much. But if the engineers who designed the GPS system didn't account for this relativistic effect, the entire system would fail catastrophically. The errors would build up at a rate of about 7 miles per day. Within a few minutes of turning it on, your GPS would tell you that you are blocks away from where you actually are. Within a day, it would be useless. So, the very software in your phone has Einstein's equations built into it. It constantly corrects for the fact that time is flowing at a different rate for the satellites than it is for us down here on the ground. It is a daily, practical, technological proof that time is not absolute. And the remarkable accuracy of this system is a testament not only to Einstein, but to the many scientists and mathematicians who made it possible. One of these crucial figures was Dr. Gladys West, an African-American mathematician who worked at the U.S. Naval Weapons Laboratory. In the 1970s and 80s, Dr. West created incredibly detailed and precise mathematical models of the Earth's true shape. The Earth is not a perfect sphere. It's a bit lumpy and squashed. Her work in modeling this shape, called a geoid, was absolutely fundamental to creating the GPS system with the accuracy it has today. Her quiet, brilliant contributions are an essential part of the story of how we brought Einstein's abstract theories of space-time down to Earth and put them in the palm of our hands. So where does this leave us? We have journeyed from the simple shadow of a sundial to the mind-bending reality of warped space-time. We have seen time as a steady, universal river, and then as a flexible, personal stream. We know that the rate at which we travel into the future is not fixed. It depends on our motion. It depends on the gravity around us. My now is not necessarily your now. Each of us is at the center of our own little bubble of space-time, experiencing the flow of time in our own unique way. And yet, our deep, intuitive feeling of time persists. The arrow of time still points resolutely forward. We still remember the past and not the future. The broken egg never unscrambles. Why? This is one of the deepest remaining mysteries in physics. The laws of relativity and even quantum mechanics work just as well forwards in time as they do backwards. But the universe we live in clearly has a preference. This seems to bring us back to that idea of entropy. The universe as a whole started in a state of very low entropy, very high order at the Big Bang, and ever since it has been moving towards a state of higher entropy, greater disorder. This unfolding, this constant increase in messiness on a cosmic scale, may be the ultimate engine that drives time's arrow forward, creating the distinction between past, present, and future that feels so fundamental to our existence. Think about it for a moment. Every memory you hold is a trace of a past that was more ordered than the present. The light reaching you from a distant star is a message from a time when the universe was younger, smaller, and in a sense, more orderly. We are all time travelers in the most profound sense. We are floating on a current that flows from a highly ordered past toward a disordered future. Our speed on this current is about 1 second per second, but we've learned this speed is not absolute. We can, in principle, slow our journey through time by moving very fast through space or by venturing into a region of intense gravity. This knowledge doesn't change the feeling of a minute dragging on when we are bored or an hour flying by when we are happy. Our psychological experience of time is a whole other wonderful mystery. But knowing that the physical reality of time is so much stranger and more flexible than it appears can fill us with a sense of wonder. The universe is not a simple clockwork machine. It is a dynamic, interconnected, evolving tapestry of space-time, and we are woven into it. The steady rhythm of your own breathing right now, in this quiet moment, is your personal clock. It is ticking away in your unique frame of reference. It is connected, through the laws of physics, to the ticking of every other clock in the universe, from the gentle oscillation of a cesium atom to the slow, grand orbit of a distant galaxy. We are all part of this magnificent cosmic dance, each of us experiencing our own unique path through the great, mysterious, and beautiful landscape of time. And so, we leave the grand, sweeping curves of gravity and relativity behind. Let us now sink even deeper, down, 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 past the scale of planets and stars, past the scale of mountains and people, past the scale of a grain of sand. We are shrinking, shrinking, until we arrive at the realm of the impossibly small, the world of the atom, the world of the electron. This is the world of quantum mechanics. And if you thought time was strange in Einstein's universe, here, in the quantum realm, it becomes a ghost, a puzzle, a stubborn, elusive character in a play where all the other actors behave in the most bizarre ways imaginable. In the world of quantum mechanics, the solid, definite reality we are used to dissolves. It becomes a world of possibilities, of probabilities. An electron is not a tiny, hard ball orbiting an atom's nucleus like a planet. It is better described as a cloud of possibility, a wave of probability that describes where the electron might be found if you were to look for it. Before you look, it is everywhere and nowhere at once. It exists in a state of superposition, a ghostly blend of all its potential states. The math that describes this fuzzy, probabilistic world is called the Schrödinger equation. And here we find our first deep, jarring conflict with Einstein's beautiful picture of space-time. In the Schrödinger equation, the foundational recipe of quantum theory, time is treated in a very old-fashioned way. It's very much like Newton's time. It's an external parameter, a background clock. It just ticks. It is not part of the system. It is not dynamic. It is not woven into the fabric of space. It's just ... time. The universal, absolute metronome, ticking away, telling the quantum wave of possibility how to evolve and change. This is a profound problem. Physics has two great theories of the universe: general relativity, which describes the very large, and quantum mechanics, which describes the very small. Both are spectacularly successful. They are the most accurate and well-tested theories in all of science. But they are built on fundamentally different ideas about time. In one, time is a flexible, dynamic player. In the other, time is a rigid, unchanging stage. How can both be true? This is one of the deepest unresolved tensions in all of physics. It tells us that our understanding is still incomplete. Let's use an analogy. Imagine quantum mechanics as a great chef, and the Schrödinger equation is their prize-winning recipe for a magnificent, ever-changing soufflé. The recipe tells you precisely how the ingredients, the waves of possibility, should be mixed and how they will rise and change over time. In this analogy, time is the kitchen timer. It just sits on the counter, ticking away. It tells the chef when to check on the soufflé. But the timer is not in the soufflé. It's not part of the batter. It doesn't get warped or stretched by how much the soufflé rises. It's separate. It's absolute. This is utterly different from relativity, where time is like a special, elastic ingredient mixed right into the batter of the universe, getting stretched and squeezed by the other ingredients like mass and energy. And the strangeness doesn't stop there. This smooth, predictable evolution of the quantum soufflé, this wave of possibility, only happens when no one is looking. The moment you try to measure something, the moment you open the oven door to check on the soufflé, something dramatic happens. The wave of possibility collapses. The electron that was a fuzzy cloud of maybe here, maybe there, suddenly snaps into a single definite location. The superposition is broken. Reality, as we know it, solidifies. This is called the measurement problem, and it is a deep mystery. But it has strange implications for time. When this collapse happens, does it happen instantly? If an electron's probability wave is spread out over a large area, and you measure it at one point, does the rest of the wave vanish at that exact same instant? This brings us back to Einstein's problem of simultaneity. What does "at the same instant" even mean? If my now is different from the now of someone moving relative to me, how can we agree on when the collapse happened? This mystery leads us to perhaps the most famous, most mind-bending, and most spooky feature of the quantum world. A phenomenon that seems to defy all our common-sense notions of space, separation, and maybe even time itself. It is called quantum entanglement. Let's try a visualization to understand this. Imagine you have a special pair of magic coins. They are linked. A quantum physicist prepares them in a special state, so that if one is heads, the other is guaranteed to be tails, and vice versa. But until you look, each coin is in a superposition of both heads and tails. It's a 50/50th possibility for both. Now, you put one coin in a box and give the other to a friend. Your friend gets in a spaceship and travels to the other side of the galaxy. Years pass. One day, you decide to open your box. You look at your coin. It's heads. At that exact moment, at the very instant you observe your coin to be heads, with absolute 100% certainty that your friend's coin, light years away, is tails. It's not that you figured it out. It's that your friend's coin became tails at the moment you looked at yours. The fuzzy cloud of possibility for both coins collapsed at the same time, across a vast distance. This is what Einstein famously called spooky action at a distance. He disliked it intensely. It seemed to suggest that some kind of influence or information was traveling faster than the speed of light, which his own theory of relativity forbade. It was as if the two coins were whispering to each other instantly across the galaxy. For a long time, physicists wondered if there was a simpler explanation. Maybe the coins were not magic. Maybe they were like a pair of gloves. If you put one in each box and send one away, the moment you open your box and see a left-handed glove, you instantly know the other is a right-handed glove. There is no spooky action. The information was always there. It was just hidden. But the universe, it turns out, is spookier than that. An Irish physicist named John Bell came up with a brilliant mathematical test in the 1960s to tell the difference between the hidden information idea, the gloves, and the truly spooky quantum idea, the magic coins. When the experiments were finally done, most famously by a physicist named Alan Aspect and his team in the 1980s, the results were clear. The universe is genuinely spooky. The coins are magic. Entanglement is real. The two particles behave as a single unified system, no matter how far apart they are. What does this mean for time? It's a question that physicists are still grappling with. It doesn't seem to allow for faster-than-light communication. You can't use your magic coin to send a message to your friend. The outcome of your measurement is random, heads or tails, so you can't control what your friend sees. You can only discover the correlation after the fact, when you get together and compare notes. So, Einstein's ultimate speed limit is safe, but the phenomenon of entanglement challenges our deepest intuitions. It suggests that our idea of separate objects, existing independently in space and time, might be an illusion, that at some fundamental level, the universe is non-local. It is interconnected in a way that transcends space. And if it transcends space, does it also, in some way, transcend time? The moment of collapse seems to happen outside the normal rules of time and space, linking distant events in a way we are still struggling to comprehend. This all leads to the final great frontier, the quest for a theory of everything. A single theory that can unite Einstein's general relativity with quantum mechanics. This is the holy grail of modern physics. It is the attempt to write down the laws of quantum gravity. And when physicists try to do this, something truly astonishing happens to time. In many of the most promising approaches, time disappears. It vanishes from the equations. One of the most famous equations in this field is called the Wheeler-DeWitt equation. We don't need to know the details. But its most shocking feature is that it contains no T for time. It describes the entire universe, all of space and all its contents, as a single, static, timeless quantum state. It describes a frozen reality. There is no before and no after. There is just ... is. This is known as the problem of time in quantum gravity. How can a timeless theory describe the universe we experience? A universe that is so obviously full of change, of flow, of a past, present, and future? The answer might be that time is not fundamental. Time might be an emergent property. What does that mean? Think about temperature. A single atom of water in a glass does not have a temperature. Temperature is a property of the collective. It's the average motion of trillions of atoms bumping into each other. Temperature emerges from the more fundamental reality of moving atoms. Or think about wetness. A single molecule of H2O is not wet. Wetness is a property that emerges when you have a vast collection of them. In the same way, many physicists now believe that time, as we know it, is not part of the fundamental furniture of the universe. Instead, it emerges from a deeper, timeless, quantum reality, much like temperature emerges from the jiggling of atoms. So let's try one last visualization for this section. Imagine the entire history of the universe, from the Big Bang to the distant future, as a single magnificent object. A four-dimensional crystal. It contains every event that has ever happened or ever will happen. The birth of a star, the formation of the earth, your birth, the meal you had yesterday, the words you are hearing right now. All of it exists frozen together in this timeless block. This is the universe as described by the Wheeler-DeWitt equation, a static crystal. So where does the feeling of flow come from? Perhaps our consciousness is like a lantern, a single point of light traveling through this crystal. It illuminates one slice of the crystal at a time. And this illuminated slice is what we call the present moment. The path of the lantern through the crystal creates the story of our lives, creating the illusion of a flowing river of time, when in fact, we are just exploring a pre-existing, timeless landscape. It's a staggering thought that the time we feel passing so intimately is a grand illusion, emerging from a reality in which nothing ever happens. This deep puzzle, the vanishing of time at the most fundamental level, brings us to the edge of physics. And at this edge, physics and philosophy begin to hold hands. The questions become as much about the nature of reality and consciousness as they are about equations. For centuries, philosophers have walked these same strange paths, armed not with particle accelerators, but with logic and thought. And it is to their world, the world of pure contemplation, that we will now drift. Let your mind settle. Let these strange quantum ideas dissolve into a gentle hum in the background. We are moving from the equations of physics to the questions of existence. Philosophers love a good debate. And when it comes to time, the biggest debate of all is about what is real. It is a debate between two ideas with grand-sounding names, presentism and eternalism, but the ideas behind them are quite simple and intuitive. Let's start with presentism. Presentism is the belief that only the present moment is real. The past is gone. It no longer exists. The memories you have are just traces, like footprints in the sand, but the person who made them is gone. The future is not yet real. It is pure potential, a mist of possibilities that has not yet solidified into a now. This is the common sense view. It's how we feel we experience reality. There is a special, unique, shining moment called now, and it is constantly moving forward, turning the unreal future into the real present, and leaving a trail of no longer real past behind it. Imagine time as a long, dark stage. There is a single spotlight shining on it. Only the part of the stage illuminated by the spotlight is real. That is the present moment. The spotlight is constantly moving from left to right. The part of the stage it has already passed over is now dark again. That is the past. It's gone. The part of the stage it has not yet reached is also dark. That is the future. It is not yet here. Only the now of the spotlight exists. This is a very comforting idea in some ways. It means our past mistakes are truly gone. It means the future is not yet written. There is a sense of openness and freedom. But then there is the other view. The view suggested by Einstein's relativity. This view is called eternalism, or sometimes the block universe theory. Eternalism is the idea that the past, the present, and the future are all equally real. They all exist. Time is not a moving spotlight. Time is more like a loaf of bread. The entire loaf, from the first slice to the last, exists all at once. Our consciousness is just experiencing one slice at a time. The slice we are currently experiencing, we call the present. The slices we have already experienced, we call the past. The slices we have yet to experience, we call the future. But the whole loaf is there. Dinosaurs are not gone. They are just in a different slice of the space-time loaf. Your 10th birthday party is still happening in its slice of the loaf. The future, too, is already there in its slices. This idea is strongly supported by physics. As we learned, relativity says that there is no universal now. If you and I are moving relative to each other, my slice of the now loaf might be angled differently from yours. My now might include something that is in your future. Your now might include something that is in my past. If all these different nows can exist depending on how you're moving, the only way to make sense of it is if all the moments, past, present, and future, are equally real. The entire loaf must exist. This is the block universe, the same frozen four-dimensional crystal we imagined in quantum gravity. This has profound philosophical implications. If the future is already out there, does that mean we have no free will? If the loaf of our life is already baked, are we just experiencing a movie that has already been made? Philosophers have debated this for a century. Some say yes, free will is an illusion. Others say no. They argue that even if the future exists, we still have to make it happen from our perspective. The fact that your choices are already part of the loaf doesn't mean you didn't make them. It's a difficult, tangled question. But the idea of the block universe gives us a different sense of our place in time. It means that our loved ones in the past are not gone. They are just in a different part of space-time. It means that moments of great joy are not lost forever. They are a permanent part of the fabric of reality. It's a less dynamic, but perhaps a more peaceful view of existence. This brings us back to the arrow of time. Why does the spotlight of our consciousness only seem to move in one direction? Why do we only experience the loaf of bread, slice by slice, from past to future? As we saw, physicists point to entropy, the idea that the universe is moving from a state of high order to high disorder. The arrow of time is the arrow of increasing messiness. But philosophers ask, is that really enough? Is a physical law about disorder enough to explain our deep psychological feeling of time's passage? Some thinkers, like the British astrophysicist Arthur Eddington, who was one of the first to champion this idea, thought so. He called entropy time's arrow and believed it was the only physical law that gave time a direction. But our perception of time is shaped by more than just physics. It is shaped by our culture, our language, and our traditions. The linear, one-way street of time, with a clear beginning, middle, and end, is a very strong idea in Western thought. It is woven into the stories of Abrahamic religions, a creation, a history, and a final judgment. It is the structure of most of our novels and films. Time is a resource. We spend it. We save it. We waste it. We run out of it. It is a commodity. But this is not the only way to see time. In many Eastern philosophical and religious traditions, like Hinduism and Buddhism, time is not a line. It is a wheel. It is cyclical. The universe goes through immense cycles of creation, existence, and destruction, over and over again. This is the concept of the yugas in Hinduism, or the Kala Chakra, the wheel of time, in Tibetan Buddhism. In this view, there is no single, unique beginning or end. There is an endless rhythm of cosmic birth and rebirth. This changes everything. The past is not simply behind you. It is a pattern that will, in some form, come around again. The future is not a final destination. It is a continuation of the cycle. This can lead to a very different perspective on life, one focused less on individual achievement in a single lifetime and more on one's place within a vast, eternal rhythm. And there are other views still. Many indigenous cultures around the world hold concepts of time that are even more different from the simple Western line. For some Australian Aboriginal peoples, there is the dream time. The dream time is not just the ancient past. It is a parallel, timeless reality that coexists with our own. It is the spiritual foundation of the world, and it can be accessed in the present through rituals, stories, and sacred places. In this view, the past is not dead and gone. It is alive and present, constantly shaping and informing the here and now. The ancestors are not figures from history. They are a living presence. Similarly, many Native American languages have a different way of talking about time. Some, like the Hopi, have been interpreted as having a language that doesn't treat time as a dimension you can chop up into past, present, and future. Instead, it focuses on the nature of events themselves, whether they are happening, have happened, or are expected to happen. The focus is on the unfolding reality, not on placing it on an abstract timeline. These different perspectives remind us that our experience of time is not just a raw, unfiltered perception of physical reality. It is a story we tell ourselves. And that story is shaped by the language we use, the culture we live in, and the philosophical ideas we inherit. Physics may describe the mechanics of space-time, but it is our human minds, in all their diversity, that give time its meaning. So let's bring our focus back from the cosmic and the philosophical. Let's bring it back into our own bodies, into the quiet, rhythmic world of our own biology. Because long before humans invented sundials or atomic clocks, life itself had already learned how to keep time. Almost every living thing on this planet, from the simplest single-celled bacteria to the tallest redwood tree, to you, lying here listening, has an internal clock. This is the field of chronobiology, the study of time in living things. Deep within your brain, there is a tiny cluster of about 20,000 neurons. It's smaller than a grain of rice. It is called the suprachiasmatic nucleus, or SCN for short. This is your body's master clock. It is the conductor of your internal orchestra. It keeps time, and it sends out signals to the rest of your body, telling it when to feel sleepy, when to feel awake, when to release certain hormones, when to raise your body temperature. This internal daily rhythm is called the circadian rhythm, from the Latin circadian, meaning about a day. This clock is not just guessing. It is a genuine, self-sustaining oscillator. It's a complex molecular feedback loop inside your cells. Certain genes create proteins. As these proteins build up, they eventually turn off the very genes that made them. Then, as the proteins degrade and disappear, the genes turn back on, and the cycle starts all over again. This whole cycle takes about 24 hours. It is a beautiful, intricate, molecular dance that is happening in nearly every cell of your body, right now. Now, this internal clock is good, but it's not perfect. If you were to live in a deep cave, in total darkness, with no clues about the time of day, your internal clock would keep ticking. But it would probably drift a little. Most people's internal clocks run slightly longer than 24 hours. So you would start going to bed a little later each day and waking up a little later each day. Your day might become 24 and a half hours long. So how does your body stay synchronized with the outside world? The answer is light. The SCN, your master clock, is conveniently located right above the optic nerve, where it can get direct information from your eyes. The light of the morning sun, especially blue light, is the most powerful signal for resetting your clock each day. It's like winding your watch every morning. It tells your SCN, okay, this is the start of the day. Let's get the orchestra in sync. This is why jet lag feels so strange. Your internal clock is still running on your old time zone, while the light-dark cycle is telling you it's a completely different time. It's like the string section and the brass section of your internal orchestra are playing from two different sheets of music. The importance of these internal clocks was championed by many scientists, including pioneers like Dr. Patricia de Corsi. In the 1960s, she conducted brilliant and painstaking experiments on flying squirrels. By studying their behavior in controlled environments, she demonstrated that their internal circadian clocks were not just a curious habit, but a crucial tool for survival, helping them anticipate the coming of night and the activity of predators. Her work helped to establish chronobiology as a serious and vital field of science. So our bodies keep a steady physical rhythm of time. But what about our minds? How does the brain create our subjective feeling of time passing? This is one of the great mysteries of neuroscience. Unlike vision, which has the eyes, or hearing, which has the ears, there is no single organ for time. The brain seems to measure time in a distributed way, using many different areas working together. Our perception of time is not a steady, constant flow. It is flexible. It is elastic. We all know the feeling. Time flies when you're having fun. An hour with a good friend can feel like a minute, but a 5-minute wait at a red light can feel like an eternity. Why is this? One of the leading theories connects our sense of time to attention. When we are deeply engaged in an activity, our brain dedicates its resources to the task at hand. It doesn't pay much attention to tracking the passage of time. So, time seems to slip by unnoticed. When we are bored or waiting for something, our brain has little else to do but monitor its own internal state, and our attention turns to the ticking of the clock. Every second is noticed, and so time seems to drag. There is another fascinating aspect to this. The feeling that time slows down during a moment of intense fear or surprise, like a car accident or a sudden fall. Many people report that in these moments, they see events unfold in slow motion. It's not that time actually slows down. Instead, it's a trick of memory. In a critical situation, your brain goes into high alert mode. A part of the brain called the amygdala kicks into high gear, and it tells the rest of the brain, this is important. Record everything. The brain starts laying down much richer, denser memories than usual. Later, when you play that memory back in your mind, there is so much detail, so many frames to look through, that it feels as though the event lasted much longer than it actually did. This leads us to the common and often poignant feeling that time seems to speed up as we get older. A summer vacation seemed to last a lifetime when we were children. Now, a whole year can feel like it passes in a flash. Why? There are a few gentle explanations for this. One is the simple math of it. For a 10-year-old, 1 year is 1/10 of their entire life. That is a huge chunk of their experience. For a 50-year-old, 1 year is only 1/50th of their life. It's a much smaller proportion, so it can feel less significant, and therefore shorter. Another, perhaps deeper, reason is novelty. A child's life is full of firsts. The first day of school, the first time riding a bike, the first trip to the ocean. Each of these new experiences requires the brain to work hard, to form new connections, to lay down those rich, detailed memories we talked about. An adult's life, on the other hand, often falls into routines. The daily commute, the weekly grocery shopping, the familiar tasks at work. The brain doesn't need to record these things in great detail. It can run on autopilot. And so, long stretches of our adult lives can get compressed in our memory into a single blurry file labeled another year at work. With fewer novel anchor points in our memory, the years seem to blend together and rush by. Our perception of time, it seems, is intimately linked to the richness and newness of our experience. From the time inside our very cells and the time inside our minds, let's now zoom out, all the way out, further than our planet, further than our sun, further than our galaxy. Let's go back to the beginning of it all, the beginning of the universe itself. This is the realm of cosmology, the study of the origin, evolution, and ultimate fate of the universe. And in cosmology, time takes on its grandest, most epic scale. According to our best scientific story, the story of the Big Bang, our universe had a beginning. About 13.8 billion years ago, everything, all the space, all the matter, all the energy, and even time itself, was compressed into a single point of unimaginable density and heat, a singularity. We cannot truly picture this. Our language and our minds fail. But from this single point, the universe began to expand. And in that expansion, space was created. And with the creation of space, the clock of the universe began to tick. This was the birth of time. What was there before the Big Bang? It is a question that fascinates us all. But from the perspective of physics, it may be a meaningless question. Since time itself began at the Big Bang, the concept of before has no meaning. The great physicist Stephen Hawking used a wonderful analogy. He said it's like asking, what is north of the North Pole? The question sounds sensible, but the concept of north only has meaning on the surface of the earth. Once you are at the North Pole, there is no more north. Similarly, once you go back to the Big Bang, there may be no more before. Time, as a direction, simply ceases to exist. How do we know this story? How can we be so confident about an event that happened 13.8 billion years ago? The evidence is written in the sky. The first great clue came in the 1920s from an astronomer named Edwin Hubble. Using the powerful new telescopes of his day, he made a revolutionary discovery. He found that almost all the galaxies in the universe are moving away from us. And the further away a galaxy is, the faster it is moving away. This is the signature of an expanding universe. It's not that the galaxies are flying through space. It's that space itself is stretching, carrying the galaxies along with it, like raisins in a rising loaf of bread. If we can see the bread expanding now, we can logically conclude that in the past, it must have been smaller. If we run the clock backwards, all the raisins, all the galaxies, would eventually come together in one place. By measuring the rate of this expansion, we can calculate how long it has been expanding. And that gives us the age of the universe. The second, and even more beautiful, piece of evidence is the afterglow of the Big Bang itself. It's called the cosmic microwave background, or the CMB. For the first few 100,000 years, the universe was so hot and dense that it was an opaque, glowing fog of plasma. Light couldn't travel freely. But as the universe expanded and cooled, it reached a point where atoms could form. The fog cleared, and the light that was present at that moment was suddenly free to travel across the universe forever. That ancient light has been traveling for over 13 billion years. As space has expanded, the light waves have been stretched out, so they are no longer visible light, but very cool, low-energy microwaves. In 1965, two American radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered this faint cosmic hiss. They were trying to use a large radio antenna for communication, but they kept getting a persistent, annoying background noise coming from all directions in the sky, day and night. They checked everything. They even cleaned out pigeon droppings from the antenna, thinking that might be the source of the noise. But the hiss remained. They had, by complete accident, found the oldest light in the universe, the faint, warm echo of creation. By studying the tiny temperature fluctuations in this ancient light, scientists have been able to calculate the age and composition of the universe with astonishing precision. So we have a beginning. We are living in the long, slow, middle act of the cosmic story. But what about the end? What is the ultimate fate of the universe and of time itself? This is a realm of speculation, but it is speculation guided by our knowledge of physics. And we must remember to approach these grand cosmic fates with a sense of gentle wonder, not anxiety. They are stories of a future so distant it is almost beyond comprehension. The most likely scenario, based on our current understanding, is a future sometimes called the heat death or the big freeze. The evidence suggests that the expansion of the universe is not slowing down. In fact, it's accelerating, pushed by a mysterious force called dark energy. In this future, the universe will continue to expand and cool and grow darker forever. Galaxies will move so far apart that the night sky of a far future civilization would be almost completely empty. Stars will slowly burn out. One by one, the lights will go out across the cosmos. The universe will approach a state of maximum entropy, perfect disorder, a cold, dark, uniform soup of stray particles. In such a universe, where nothing ever happens, would time still have meaning? If entropy is the engine of time's arrow, then in a universe at maximum entropy, the arrow would have nowhere left to point. Time, as a meaningful flow, might simply ... cease. It would be an end of unimaginable stillness, a peaceful, eternal twilight. There was another idea, for a long time a popular competitor, the Big Crunch. In this scenario, if there was enough matter and therefore enough gravity in the universe, the expansion could eventually slow down, stop, and reverse. The universe would begin to collapse back in on itself. Galaxies would rush towards each other, heating up until everything was crushed back into a hot, dense singularity, just like the one from which it began. This idea is poetically satisfying. It opens the door to the cyclical models of time we saw in philosophy. Perhaps our Big Bang was the result of a previous universe's Big Crunch. Perhaps the cycle repeats, endlessly, a cosmic bounce. While current evidence makes this less likely, it remains a beautiful and powerful idea. There are other, more exotic possibilities that scientists ponder. Ideas like the Big Rip, where the accelerating expansion becomes so strong it tears apart galaxies, stars, planets, and even atoms themselves. These are the kinds of thoughts that occupy the minds of cosmologists as they gaze out at the vastness. They are not predictions of our doom, but rather explorations of the ultimate limits of the physical laws that govern our reality. And so we bring our journey to a gentle close. We have traveled from the simple and intuitive idea of a universal clock, ticking steadily for everyone, everywhere. We saw how Newton built a magnificent clockwork universe upon this foundation. Then we journeyed with Einstein into a stranger, more flexible reality, where time is woven together with space, a fabric that can be stretched by speed and warped by gravity. We saw how your own personal time depends on how you move and where you are. We then dove into the bizarre quantum realm, where time becomes a stubborn background parameter, and where the very notion of time seems to dissolve in the ultimate equations of reality, perhaps emerging as a grand illusion from a timeless state. We have listened to the long conversation of philosophers, debating whether only the present is real, or if all of time exists in a great silent block. We have seen how different cultures have told different stories about time, as a line, a wheel, or an ever-present dream. We have looked inside ourselves, at the tiny, ancient clocks ticking in our cells, and at the wonderfully elastic timekeeper of our own minds. And finally, we zoomed all the way out to the beginning of time in a cosmic dawn, and pondered its long, slow fade into an eternal, quiet night. What is time, really? The truth is, we still do not know. It is not one thing. It is a concept that changes depending on the scale we look at. It is the steady beat of the physicist's equation. It is the flexible geometry of the cosmos. It is the irreversible arrow of entropy. It is the deep structure of our stories. It is the rhythm of our bodies. It is the subjective river of our consciousness. The search for a single, unified understanding of time remains one of the greatest challenges in all of science and philosophy. It is a sign that there are still profound, beautiful mysteries waiting to be explored. And perhaps the most wonderful thing of all is that we, as conscious beings, get to experience it, this simple, flowing, present moment. This act of being here, now, this quiet miracle of memory and anticipation. This is our little slice of the great cosmic loaf, our brief, shining moment in the lantern's beam as it moves through the vast, silent crystal of what we call time.